So I want to talk about locked compressors, compressors that are not turning, and this also applies to blower motors and condensing fan motors and all this as well. What do you do, or first off, let's just start with, how do you know that a compressor is locked versus some other type of problem? What are some of the telltale signs of a locked compressor? So it draws locked rotor amps. Locked rotor amps, what does locked rotor amps mean?
Significantly higher amperage.
So really high amperage, right? And usually it only draws locked rotor amps for seconds, very, very short period of time. And so when you think about locked rotor, the term locked rotor amps, within a motor, you have the rotor and you have the stator. And the easy way to remember that is the rotor is the one that rotates and the stator is the one that stays stationary. So it's pretty straightforward, pretty simple, right? So if you have a condensing fan motor, the part that's attached to the shaft that actually spins is which one? The rotor. And the part that creates the electromagnetic field that spins the rotor is called the stator, right? So when we have a locked rotor amps, what does that mean? It means the amps that it draws when the rotor is locked. And why does it draw higher amps? This is going to get a little bit techie, but this can help us remember some of these things if you can lock it in. Why does it draw higher amps?
Because there's no resistance, because the resistance is created by the spinning, right?
The resistance is created by that rotational field. Does anybody know what the name of that type of resistance is?
Inductive resistance.
Inductive reactance. Very good. Inductive resistance I would accept. I would accept. He's on fire this morning. So yeah, inductive reactance. And what that means is, just very simply, is that when we, for example, when we energize a light bulb, right? We run current through a light bulb, we apply a potential difference, otherwise known as a voltage, to a light bulb. The resistance that exists is the resistance of that filament, right? Now, a little kind of fun fact is that the filament resistance in a light bulb is actually significantly higher once the filament heats up than if you were to test it with the bulb cold. That's a little fun fact. So if you ever were to take an ohm reading, if you wanted to get really fancy with Ohm's law and you took an ohm reading on a bulb and you're like, oh, okay, well now I can figure out what the amperage is. Wrong, because the resistance of that filament is actually about 10 times higher, thereabouts, when the filament heats up than when it's cold. So that's another kind of weird thing that happens. But in a heat strip or in any sort of a resistive load, that resistance stays fairly fixed once it's actually up to temperature. Whereas in a motor, anything that's what we call an inductive load, where it uses magnetism, it has to have that back EMF is produced, which creates inductive reactance. And all that means is that the resistance don't show up until the motor is spinning up to speed. And that's why when you first check the current, you see higher current because there's lower resistance. Less resistance to electricity means more of it moves, right? So that's what you're seeing. And in the process, it also heats up really fast in the windings. And why is that? Well, it's because when the windings don't have that resistance, that back EMF, inductive reactance, doesn't show up, then those windings basically become electric heaters. And that's why you have this overload, and the overload is positioned in the windings, so that if those windings start to heat up, it cuts it out really quick. Overheats, opens the switch, shuts off the motor. And those exist in blower motors, those exist in condensing fan motors, those exist in compressors. And so when you have a locked compressor, what you find is a compressor that's overheating. But it's overheating because the windings are heating up, and the windings are heating up because the compressor's locked, right? Make sense? Now, unlike a compressor that shuts off when the system is low on charge, if you've ever found it gone up to a system in the middle of summer and the compressor's not running, and you touch the top of that compressor and it's flaming hot, right? When you run into those conditions, that's usually what we call an operational overload, meaning that the thing overheated while it was running. And those get really hot. The whole shell gets hot, everything gets blazing hot. Whereas an overheat that occurs because the compressor's locked, the compressor doesn't get nearly as hot because the heat is generated in the windings. So back up to kind of what I'm talking about here. When a compressor is flaming hot, you can touch the shell and you can feel that it's really hot. What most likely caused that? We gave an example, low charge is one cause. Not a bad capacitor is an electrical fault, so that's going to cause the heat to be contained in the windings mostly. Failed fan motor, failed condensing fan motor could be, right? Could be a really dirty condenser. Anything that causes that compressor to run hot is going to obviously eventually cause that sort of overheat overload if it gets bad enough, right? And we've talked about compression ratio in the past. High compression ratios are generally what cause that operational high temperature. And so high compression ratios can be low suction pressure or high head pressure. Either one of those two things causes high compression ratios, because compression ratio is the difference between your suction pressure and your head pressure. So suction pressure too low causes the compressor to overheat because it needs that refrigerant returning back to that compressor in order to keep it cool. Head pressure too high can cause that. So like we said, failed condenser fan motor, dirty condenser, severe overcharge, severe undercharge, anything like that, a restriction in the system that's not allowing enough refrigerant to come back to the compressor, all those things can cause that operational overheat. But the reason I'm telling you this is because that's operational overheat. If you go up to the compressor and you touch it and it's blazing hot, not a locked compressor. If the compressor were locked, it couldn't get that hot because that thermal overload is located in the winding. So if the winding's overheating, it's going to take it out like that, and that's what you see with a locked compressor. Or a system that has a bad capacitor, as an example. If you go up, pretty consistently, that compressor is going to be a little while later, 30 seconds later, 45 seconds later, a minute later, right? And it only tries to run for a short period of time, and it's immediately taking it out. That makes sense? Because that's winding generated heat, not operational getting too hot because it's running hot because of high compression ratio. Make sense? So this is not even taking measurements. A lot of people say, well, I measure locked rotor amps. Locked rotor amps isn't by itself a very valuable measurement. Now, there's people who will argue with me about this, and we've talked about this recently in another class. Not super valuable because, and it comes down to the ways that different meters measure and how quickly they measure and all that. So comparing one meter to another, you're going to get different readings. You could take 5 different amp meters, check locked rotor amps on the same compressor, and read something completely different with each one. Right, that's gonna happen pretty consistently, especially typical start amps when a compressor first starts up. But what we do know is that when you go up to a compressor and it's going, it's locked, right? It's not spinning. So what do we do about it? This is what I want to get to. What do we do about a locked compressor, a compressor that's not spinning? Well, we can put one of these on it. This is a aftermarket hard start kit. Okay. And we stock these. So I am not, contrary to popular belief, I am not against hard start kits. In situations where a compressor is locked and everything else is as it should be. But do we go to this first? No, what do we check first? Check a capacitor. What else do you check? Incoming voltage, that'd be a good one. What else do we check? What's that? Ohming out the compressor you could, but if the compressor wasn't ohming out, meaning if it didn't have proper, or at least some resistance in between the windings, if a winding was open, for example, it wouldn't be trying to start. So if we hear it trying to start, we know that at least the windings are intact to some degree. Now, could it be that just the start winding is open? Possible. Fairly rare, but possible. So you could do that. I would do some visual inspections first. So I would start by looking at all your wiring connections, making sure that the run capacitor that's installed is the right size, making sure the run capacitor isn't failed, obviously. Tracing back the wires, looking to see, does this compressor look new? Did somebody maybe put a different compressor in and so now the run cap isn't a match anymore? I would be paying attention to how it's wired, making sure that the right terminals are in the right connectors. Especially, again, we don't always know. Another company may have been here, the homeowner may have tried to do something themselves, so pay attention to all that. Then definitely look at the terminals on the compressor for sure. Because if you have, for example, the terminal that's connected to the start terminal on that compressor, the start winding, if that's melted off or not connected, then that would also cause it. Because a failed capacitor and a wire that's disconnected on the start winding, it gives you the exact same result. And on most compressors, they're not going to start if you don't have a run capacitor in place, right? If it's not wired up right, if it's not connected to the compressor, it's not going to start. From there, you could go ahead and ohm out the compressor and just make sure you don't have an open start winding. That could possibly do it, but in most cases, that's not going to be the case. So you're going to go through, you're going to do visual inspections, you're going to check your run capacitor, you're going to make sure it's the right size, you're going to make sure there's no hanky-panky going on, with somebody miswiring something, putting in, this is a brand new compressor, somebody did something weird here, all that kind of stuff. You're going to want to make sure. You're going to want to confirm incoming voltage. Because it could even be somebody could have put the wrong compressor in, maybe the wrong voltage, or maybe put a 3-phase compressor in for single phase. All kinds of weird stuff like that can happen, and you want to have your mind open to all those possibilities, just to make sure that it's all correct. Now again, you walk up to the system, it's clearly the same compressor that's been in there the whole time. You can look at the braze connections and tell. Then at that point, you're not going to worry as much about that, although anything is possible, of course. Once that's all said and done, then you're going to go to a hard start kit. Now, are you going to go, let's say this unit is 3 months old and it has a locked compressor. Are you going to put a hard start kit on it? Trick question, you are, right? And why are you going to?
See if you can get the unit right.
You want to try to get it running, right? You're not going to leave somebody without air just because you want to be all dogmatic about not using an aftermarket hard start kit. Now, let's say that it is a new system and you put this on there and it does start running. Now what are you going to do? What are you going to do? Well, you're going to need to get, again, we're talking about, in this example, it's a unit that's under warranty. We installed it, right? 3 months old, something like that. You're going to want to look at why. Why did this need this? Is it because it was a long line application potentially? Or do we have under voltage? Is it a 208 building, like this building? There's 208 volts incoming. You're going to be more likely to have locked compressors in a case where the voltage is lower to begin with. And so you may just say, okay, let's go ahead and put in a factory hard start kit. This thing should have had a factory hard start kit to begin with. It's got a hard start off TXV. It's got long lines. This goes to another class that we've already done about long line considerations. It's on the YouTube channel. If you have no idea what I'm talking about, you can find that one. But in a lot of cases, the factory actually says this should have a factory hard start kit. So do we leave this on? Well, we may leave it on for now in order to keep the customer with air. We're not going to leave a customer without air, but we're going to go back and put in the factory hard start kit in that case. And why is that? Why is the factory hard start kit superior in most cases to an aftermarket hard start kit? Anybody know? It's not because there's anything wrong with the aftermarket hard start kit. There's nothing like fundamentally flawed about an aftermarket hard start kit. It's just that the capacitor and the relay have to be designed for a wide range of compressors. They're not designed for this specific compressor. And so what that means is that either we're underdoing it or we're overdoing it. And there's two ways to underdo it or overdo it. One is, because this relay is designed when that compressor gets up to about 80% speed, and that has to do with what we call back EMF, which means that, just quickly for those of you who are nerdy and want to understand how this works, I saw your face light up. When that motor starts spinning, it actually not only is receiving current, but it's actually producing its own energy as well. It actually acts simultaneously as a motor and a generator. Okay, because it has this rotating magnetic field and there's an interaction between the rotor and the stator. And so it actually acts as a generator as well, and it creates this thing called back EMF. And that back EMF, that back electromotive force, actually increases as that motor spins faster. And that's what energizes the relay on this potential relay. And it's a very, this is a very touchy business. Fine differences can make a big difference in how long this start capacitor stays in place. This start capacitor is only adding current to the start winding. It has nothing to do with the run winding. And so it's supposed to come out of the circuit. That's why we have this relay. We don't want this big boy staying in there at 150 microfarads or 200 microfarads or whatever it is, right? That's too much current for that start winding for it to run all the time. So this relay's got to take it out. But let's say that this relay is set up so that rather than it taking it out at 80% of the motor speed, it's waiting till it gets to 95% to take it out. That means it's staying in too long. That means that the start winding is getting hotter than it should be getting. It's not good for the compressor. Now let's say that, well, okay, to be safe, they take it out early, which is what they tend to do with these because they don't want to overdo it. Well, now they underdo it. So now it takes it out at 70% of motor speed rather than 80%. Well, now it's not as likely to keep starting consistently. The other thing is the size of the capacitor, the microfarads of this start cap. We're using an aftermarket, so it's just one size for multiple different tonnages, multiple different compressors. Well, a scroll compressor versus a reciprocating compressor, all these, they would require different microfarads. And only the manufacturer knows which one is the exact right match of relay and capacitor for this compressor in order to get it to 80%, take it out, no more current than we need, just enough, not too much. Too much is bad, too little's bad. And so that's the downside with aftermarket hard start kits. So why do we keep them? Well, the reason is because for a system that's out of warranty, to wait and come back with another capacitor and the costs and all that, we're just trying to get some more life out of a unit. Getting some more life out of a locked compressor that's 10 years old, 12 years old. This is great. Awesome. Keeps Mrs. Jones' compressor running. Now, when we put one of these in, do we say, everything's good, see you later? Is that what we do? What do we do? Give them what's the truth?
Locking compressor, did a last minute 5-second effort to get it running. Can't tell you how long you have, but
Yeah, but start saving your money, right? If you'd like to have Tyler come out and give you a quote on a new system, we can gather some information and get that over to him, right? Right? No?
Would we just replace the system? Do we still have Tyler come out?
No, we do not. I just said 10-year-old system, keeping it running a little bit. That's what I'm saying. Key distinction between system we installed, system somebody else installed, system we installed under warranty, system somebody else installed that's under warranty, and a system that's out of warranty. Those are all three different animals. Let's say somebody else installed it, and it could use a factory hard start. We put this in, we charge them for it, and we tell them, but we recommend going back in with a factory hard start kit, and we write that up, and we give that to Buddy. And then they get a quote to put that factory hard start kit in with the reasons why. Now we know, right? The reasons why is it's better for the system to go back. Now the customer chooses. They want to go back with the factory. They don't want to go back with the factory hard start kit. They're paying either way. We don't care the fact it's under warranty, because even if it were, that would have been an additional add-on initially. They're going to say, well, I thought it was under warranty. Yes, but the factory hard start kit doesn't come in the box. It's an add-on, right? In the same way that this is. If it's out of warranty, then we just leave this as the solution at that point. We're not going to waste a customer's money to go back and put in a factory hard start if the thing's 10, 11, 12, 13 years old.
Why does it seem that trained systems and American standards don't work with most universal hard start kits?
And this comes down to the fact that they require a significantly different capacitance and a significantly different potential relay. And it's just that they need more. Those things are monsters. So we're not talking about the train scrolls, because they have the orange scrolls, but then they have the orange Tylers. And again, I'm talking out my butt here because I have not looked at the spec sheet, but to your point, I've observed the exact same thing. Train factory hard start kits, go back in with a train factory hard start kit. If it's a multi-speed unit, you got the old Bristols that run one way and then run the other way in order to get the two different stages out of the equipment. I said multi-speed, I should have said multi-stage. If it's anything weird, only go back in with the factory hard start. Don't even try to use this if it's some sort of strange configuration, because there's a lot of different stuff out there. But your typical single speed equipment, if it doesn't have one, then even on a train, if you're going in and it didn't have one before, then you can try to use this to get it started. It may or may not work, but you can at least give it a shot. And again, we're talking about, you guys have all seen those giant orange compressors. They're just beasts. Does that make sense? Do you all kind of get that? So do we like aftermarket hard start kits? Sure, they're great in their proper use. Now, I recently did a podcast with a company that makes soft starts, which is a totally different thing. If you've got a client where the lights are dimming, or they're on solar, or they're on a generator, then we should be quoting people a soft start. Completely different animal. Rather than starting it quick and fast and hard and getting it running quick, it actually modulates the current into the compressor to start it slowly, like we do with a variable speed system. Like we do with an Infinity or any sort of inverter-driven equipment. If you're ever seeing that, client has solar, client has a generator, that's a great, nice little upsell that's of a great value to them. Because they may, their generator may not be able to run the system if it's got those locked rotor amperage when it first comes on. We can say, hey, we'll put a soft start in, not a hard start, a soft start, so that way it starts slowly. They're not cheap. They're expensive, so it's not the sort of thing you're probably gonna, everybody's gonna go for. But you can at least offer it to them, like, hey, this will make it run a lot better with your generator, and it'll run better for its whole life too. It'll run lower heat and likely increase the longevity of the equipment. Go ahead, Tyler.
do you have a particular brand that you like to use the most?
Yes.
I'll get with you on that.
Well, just look at my YouTube channel about 3 videos back, because we did a whole thing, and all of a sudden my mind is.
What channel is it?
It's called HVAC School. Yeah. Yeah, it's called HVAC School. So, because there are about 3 or 4 different companies that make them, and they're very effective. There's no question about their effectiveness. And they don't hurt anything, because it's kind of the opposite thing. Rather than hitting that compressor with a bunch of current that could damage it, you're kind of slowly modulating the current to bring it up to speed. And you don't have the lights dimming, you don't have some of those other issues with generators and
It's also guaranteed to make your compressor last forever.
No, that's not, no, we don't say that. We don't say that. All right, thank you all, appreciate you.
Thanks for watching our video. If you enjoyed it and got something out of it, if you wouldn't mind hitting the thumbs up button to like the video, subscribe to the channel, and click the notifications bell to be notified when new videos come out. HVAC School is far more than a YouTube channel. You can find out more by going to hvacrschool.com, which is our website and hub for all of our content, including tech tips, videos, podcasts, and so much more. You can also subscribe to the podcast on any podcast app of your choosing. You can also join our Facebook group if you want to weigh in on the conversation yourself. Thanks again for watching.